Okay. Hi, everyone. This is our final project for modeling complex systems for simulating interaction growth in social platforms. My name is Max.
I'm Gian.
And Jay.
Right. So, to introduce this, I'm sure you're all familiar with social platforms to some degree. Those are things like Facebook or Reddit or Twitter. Um, and as with the growth of the internet in the last several years, there's also been growth of these social platforms. Fundamentally, of course, these are made up of different users, but they give way to larger emergent structures that typically follow a hierarchy, as you can see over here on the right. And the interactions between users um, and their collective behavior give way to some emergent system properties that we are aiming to analyze in this project. So to set the stage, there's lots of work that has been done in this context, typically following a network structure. Some results include the discovery of scale-free preferential attachment, which basically indicates that at any scale that you're looking at within the entire social platform, you tend to see the same degree distribution. But we wanted to focus more on those group structures rather than the user to user interactions. And in order to do that, we wanted to look at how they interact in those groups instead of with each other. But we also wanted to be able to capture the user's group preferences and for the sizes of those different structures. For our simulation, we did analyze this stuff over time. So we aim to answer these questions of how the group structures grow over time and how the user's preferences change over time.
Yeah, so to give a little bit of background and justification for our model, we basically, yeah, like for what Max was saying, because we're not modeling user-user interactions, there's no point in adding a network structure to our model to unnecessary complexity or cellular automata to that matter. Also, since we're going to be combining a bunch of different processes, we came to the conclusion that writing a differential equation and a system of differential equations would be too complicated to feasibly do. Having individual agents also gives us more control over what we can have them do in terms of mechanisms to employ. An additional feature of this model that we wanted to focus on was the stochasticity of such events. Making some of these rates variable allows for more fluctuations in user and group level interactions, which leads to more interesting dynamics, the positive feedback loop in that case. Yeah, but there are also a couple assumptions that we need to clarify for our model to because we wanted to simplify it a lot. And so one of these assumptions is that these agents are homogeneous, and the way in which that they modify their baseline preference distribution is also uniform in nature. And another assumption we made is that each user has the same probability of interacting at each time step, which is a flawed but useful assumption because it makes way less. We need way less parameters to keep track of.
As for the model logic, this is sort of just me going to be going over some pseudocode to give you a brief understanding of what the model or the simulation itself looks like. We initialize a set amount of users, groups, and communities that we're going to look at on the next slide, and we're going to make sure that each group or each community has at least one group, and at least every group has one user. And then for every time step, we basically just did 100 every single time. We're going to have new users and groups join the simulation, and for each new group, we're going to have a chance for them to form a community. And if they form that community, they're going to join it. If a new community gets made, we give each user a chance to join that new community or that group that formed the new community. After all of that, we're going to have each user have a chance to join any group they're not in. Then they're going to interact with a group based on their preferences, which we will talk about, and they're going to potentially interact with other groups within that same community, and then we're going to update the preferences, and we're going to continue that.
Yeah, and so this is just a brief overview of parameters and hyperparameters of our model. I'm gonna go over a few of them, but they're all here just for brevity's sake. So the more important parameters that we wanted to tune and look at were the user growth rate, which is the number of new users at each time step, and the new group rate, which is the number of new groups at each time step, and how these two parameters contributed to dynamics of how the overall interactions of the system changed. We also were looking at the new community chance, which is the probability that a new group makes a new community, and then obviously the interaction chance itself, which is what is the likelihood that a user interacts at each time step. Some of the initial condition parameters that we specified were the number of initial users, groups, and communities, which is listed up on the right. And then those alpha and beta hyperparameters were for the preference distribution mechanism.
Okay, so here we have an example of one run of our simulation. We ran this one for 1,000 time steps instead of 100 using the following parameters for the simulation. And if you look at the figure on the left, it indicates one of our assumptions that each user has basically a uniform chance or rate of interacting. So as you can see, the user ID at the bottom on the x-axis can be thought of as the age of each user. So user 0 is the oldest one. And as you can see, it's a linear decrease. So if they were all born at the same time, they would all probably have a similar cumulative number of interactions. But despite that, it does give rise to seemingly some emergent properties in the other two figures, where despite having the same increase over time with groups, where generally the oldest groups are the largest, it is not the same linear decrease as you see with the users, where the overwhelming majority of them have little to no interactions, where a few of the oldest ones for that matter, seem to have an overwhelming majority of the total number of interactions, which appears in this graph to follow something akin to a power law distribution. And there's a similar phenomenon with the growth of each community over time, where, again, the oldest ones tend to be the largest ones at the end of the simulation. However, they don't all grow at the same rate, where you can see that, this is also, it's worth noting that the y-axis is in log space, but towards the end of the simulation, the largest groups contain an overwhelming majority of the total number of interactions as compared to the rest of them, which have comparatively few, with some of them even ending with as few as just over 100 interactions.
Yeah, and so another area of our model that we wish to examine and validate was our user preference mechanism and looking at how user preferences change over time. And to that point, we ran a new iteration of our model and tracked an initial user's preferences over the length of the simulation. And so if you look at these plots on the bottom, you can note how initially this user is in group 3, and then they also join group 7. They have a 50% chance of either interacting in 3 or 7. It then shifts in the next 15 time steps so that they actually prefer group 7. But then over the next 30 time steps, there's a lot of divergence. And now not only does this user also interact in group 8, but majority interacts with group 3. And then at time step 90, which is that last plot in the bottom right, you can see that there is even more shifting of preferences. And so this is actually a pretty interesting result, like this specific user, because you're able to see that while its initial preferences, which is maybe interacting in group 7, took precedence, the sheer size of group 3 dominated the user's preferences by the end of the simulation. And you can see that in the plot in the upper right, where group 3 is the most interacted in group. And this can be seen as an emergent property of the mechanism.
Next, we wanted to take a look at some varying parameters. We wanted to vary some parameters to see if the simulation would change. Something to note is that each graph here is showing 50 simulations of the same exact parameters. So each one is going to show 100 total, 50 for each. The first one, we're looking at user growth rates. So we're looking at a expected value of 2 new users per time step, or 0.5. With more users, that's going to give us more interactions in total, which is going to give us larger groups. And we see that in our mean of 318 compared to 174. It's got a much higher high end too, with some very large 2,000, 3,000 interaction groups too. Looking over at the interaction chance, we're checking 100% interaction chance with 20%. So what that means is the user either has 100% of interacting each time step or 20%. And with a higher interaction chance, that's just going to give us more interaction total, and we can see that here. Something interesting to note is that the mean of 335 for the high interaction chance is almost exactly 5 times the low interaction chance mean of 68, and that sort of follows because our high interaction chance is 100%, low is 20%, which is also the same ratio. Following that, we're looking at the new group rate. So it's either a new group where an expected number of new groups equal to 0.5 every time step or 0.1. More groups means that there's going to be less, there's still the same amount of users and comments per se across a larger range of groups, which means these groups are going to be on average smaller, and we do see that 129 compared to 179. And lastly, we've got a new community chance of either 50% or 10%. This one isn't as strong of an effect as the previous one, but we do note that the mean is still lower on the higher new community chance, showing that the same amount of resources over a larger amount of things is going to result in a lower overall mean.
Yeah, and as good as we think our modeling choices and execution were, there are obviously some limitations and room for improvement. One limitation is that our model has uniform user preference distributions and interaction thresholds, which is nice for computation speed, but does not actually tell you what's going on. So future work would involve us adding a new mechanism of specifying user level preferences as well as varying interaction thresholds for each user. Additionally, this model does not focus on user-user interactions. So another avenue that we can take our future work is going one step down in the hierarchy and actually modeling user-user interactions. One which way we can do is to have it be an interaction network mechanism where users create threads and can either respond to the original post or some other person in some branch of that thread. That would also unlock the ability for us to do network analysis and analysis of those metrics of those networks, which would be included. One last thing that we could do for our future work as well is to include a hypergraph mechanism in which a group would be considered a hyperedge, and then you could have local user level interaction networks within each hyperedge. And that is all we got for the future work.
So, in conclusion, we were able to simulate what we tried to when we set out, which is some sort of social media platform and a social media platform that gives rise to preferential attachment. We also checked off other boxes where we were able to simulate the updating of user preferences. So they start out with a sort of randomized preference, and they start to cater towards what the majority of people also follow, shifting towards larger structures over time, larger groups, larger communities. Finally, sweeping over our parameters yielded some really interesting comparisons. A lot of the stuff that we saw in the parameter sweep follows what we would intuit is true, which is sort of good and makes us believe in our model and its accuracy and its output. Otherwise, that's it. Here are references. Thank you.
Take care.